Hi, welcome back to my channel. My name is Gina. Today in this video we're going to prove the power rule. In the last video when I talked about calculus, we've proven the derivative of x squared using the definition of derivative. If you want to review that video, I'll put the link up there. So today we're going to prove the derivative function when the function is x to the power of r, where r can be any real fixed number. As I mentioned at the end of the last video, a derivative function of x to the power of r is r times x to the power of r minus 1. So now let's prove when the r is a positive integer. Before I start to prove it, let's note the following pattern. So I think most of the people are more familiar with the first two, the differences of squares and differences of cubes. When you have differences of squares, you can simplify that as a minus b times a plus b. And when you have differences of cubes, you can simplify that as a minus b times a squared plus a times b plus b squared. And this pattern can actually continue forever. So at the end, we got a form of a to the power of n minus b to the power of n, and now it equals to this. So let's remember this pattern, and now we're going to prove the power rule. So we're going to start with the definition of derivative function. So for f of x equals to x to the power of n, the derivative of that is limit of the change in y over the change in x. So consider the 2 points in x is x and a. So the change in y would be f of x minus f of a, and change in x would be x minus a. And since we are looking for the slope of the tangent line, so we want to make the 2 points really close to each other. So we are taking the limit as x approaches a. Now we substitute the f of x and f of a into the function. So this equals to limit of x to the power of n minus a to the power of n over x minus a as x approaches a. Now in the denominator we have x to the power of n minus a to the power of n. So we can use the pattern that I just mentioned. So this equals to limit as x approaches a of x minus a times x to the power of n minus 1 plus x to the power of n minus 2 times a plus x to the power of n minus 3 times a squared, and so on, plus x times a to the power of n minus 2 plus a to the power of n minus 1 over x minus a. And the x minus a in the numerator can cancel out with the x minus a in the denominator. So this equals to limit of x to the power of n minus 1 plus x to the power of n minus 2 times a, and so on, and plus x times a to the power of n minus 2 plus a to the power of n minus 1. So now if we use the chain rule, we'll get a to the power of n minus 1 plus a to the power of n minus 2 times a plus a times a to the power of n minus 2 plus a to the power of n minus 1. And note that if we have a product of two exponential functions where the base is the same, for example x to the power of a times x to the power of b, then this equals to the base x to the power of the sum of the exponents, so x to the power of a plus b. So this equals to the first term stays the same, a to the power of n minus 1, plus the second term here we have a to the power of n minus 2 times a to the power of 1. So this equals to a to the power of the sum of the exponent, which is n minus 1. And plus, here we have a to the power of 1 times a to the power of n minus 2. So this equals to a to the power of n minus 1. And the last term is a to the power of n minus 1. And note that here we have n terms. So this equals to n times a to the power of n minus 1. So now we've just proven that if a function equals to x to the power of n, where n is a positive integer, then its derivative function is n times a to the power of n minus 1. This pattern will also work with any real fixed number r. So for a function equals to x to the power of r, then the derivative is r times x to the power of r minus 1. Let's look at a few examples. For f of x equals to x cubed, the r for this function is 3. So its derivative function would be 3 times x to the power of 3 minus 1, which equals to 3 times x squared. For the next function, we have square root of x. So we want to rewrite this in the form of x to the power of r. And square root of x equals to x to the power of half. So in this case, the r is 1 over 2. So its derivative would be 1 over 2 times 1 over 2 minus 1, which equals to half times x to the power of negative half. Or you can rewrite this as 1 over 2 times square root of x. And for the next function, we have 1 over x squared. And again, we want to rewrite this in the form of x to the power of r. So let's rewrite this as x to the power of negative 2. So r is negative 2. So its derivative would be negative 2 times x to the power of negative 2 minus 1, which equals to negative 2 times x to the power of negative 3. And then for the next function, we can rewrite this as x to the power of 3 over 5. So r is 3 over 5. So its derivative would be 3 over 5 times x to the power of 3 over 5 minus 1, which equals to 3 over 5 times x to the power of negative 2 over 5. And then the last example, we have 6x squared. But we want the form of x to the power of r. So let's rewrite this as 6 times x squared. And if we have a constant in front of a function, then its derivative will simply equals to the constant times the derivative of the function. And this rule is the constant multiple rule. So the derivative function for this f of x equals to 6 times the derivative of x squared. Now we can use the power rule to the x squared. So this equals to 6 times the derivative of x squared is 2 times x. So this equals to 12x. I hope this video helped you to better understand the power rule. If you have any questions, feel free to comment below. And I'll see you in the next video.